In this video, we're going to introduce the class of graphs referred to as conic sections. So the conic sections are so named because each is formed when you slice a plane, in other words, just a flat two-dimensional surface, through a doubled cone, what we refer to as a double napped cone, in various ways. So we can slice a plane through the cone in different ways, and we look at the cross-section of where the plane and the cone intersect, and that's going to form one of four curves. So the simplest curve we get is a circle. So if you were to pass a plane through the cone, through either the top or the bottom of the cone, so that it is essentially perpendicular to the axis of the cone, which is what goes through the center of the cone, then the cross section is shaped like a circle. Now if you were to take that perpendicular plane and then slant it a little bit so that it passes through diagonally but also passes through both sides of the cone, then we have what we call an ellipse, which is what we're going to talk about in this video. If you were to pass the plane through the cone vertically so that we are parallel to the axis of the cone, then notice it's going to slice through the cone in two locations and we end up with two open curves. This is what we call a hyperbola. So a hyperbola graph has two separate branches formed when we slice that plane through the cone in those two locations. And if we take that plane and then angle it diagonally so that it's not parallel to the cone's axis but to the edge, one of the edges of the cone, then we have what we call a parabola, which you're probably familiar with. So in this video, we're going to talk about ellipses. We'll talk briefly about circles, and then in the next two videos, we're going to talk about the hyperbola and the parabola. So let's just start with a circle, since that's what we're familiar with. We'll just formalize a little bit, and then we'll focus on the ellipse. So formally defined, a circle is the set of all points in a plane that are r units away from a fixed point, what we think of as the circle's center. So every circle has a center, and the actual circle itself, the graph we draw, is the set of all points that are the same distance away from the center, specifically r units away from the center of the circle. So r we refer to as the circle's radius. And of course, if we double r, we have the circle's diameter. So we have two different forms of a circle's equation, and we write each depending on where the circle is centered. We're going to focus on the same two kinds of equations for all of our conic sections. So either we focus on something that's centered at the origin, or we focus on the type of equation that results when we move the center to another location in the coordinate plane. So if our circle is centered at the origin, then its equation is of the form x squared plus y squared is equal to r squared, where r is the radius of the circle. And then if our circle's center moves to a different location in the coordinate plane, essentially we adjust x and y, and so we'll have x minus h squared plus y minus k squared is equal to r squared. So the ordered pair h comma k is going to represent the center. So keep in mind, if we had addition in our actual equation, then we think of h and k as being negative numbers. Subtracting a negative results in addition when we actually write out the operations. So in this case, we have a circle of radius r, but its center has been relocated to a point other than the origin. So if we were to think of this particular form as having a value of h equals 0 and k equals 0, then we would have the original form where we're centered at the origin. So here's the general idea with a circle if we want to be a little bit more formal. Now, if we take a closed curve similar to a circle, but give it two fixed centers instead of one. In other words, instead of a true central point, imagine two central points. And then we draw all the points such that the sum of the distances between the points we draw and the two centers, those fixed points, if we set that to be a constant value, the sum of the distances between the points we're drawing and the centers, then essentially what we draw is an oval curve, what we refer to as an ellipse. The two centers, not truly centers, but kind of what we think of as centers, are called foci. which is the plural of focus. So it's hard to envision what the sum of distances being constant would look like. But here's a picture of essentially what it would look like, and it shows you how you could actually draw an ellipse on your own. So if you were to imagine placing a string onto a flat surface and pinning the string down with two push pins, and then placing a pencil, pen, some type of writing instrument against the string and pulling it tight, and then tracing around while keeping the string pulled tight, then essentially you've created a distance 1, a distance 2, and since the length of the string doesn't change as you continue to trace around and keep that string pulled tight, the total distance, the sum of those two distances, remains constant. And so all of the points you draw as you rotate around, one distance may shrink while the other distance may grow, but the sum of the distances is going to be the same. So that particular curve that we trace in that manner, and of course we could flip the string, pull it downward, and trace everything below. That curve is what we call an ellipse. So essentially you can think of an ellipse as a circle that has been elongated in a particular direction. Now keep in mind that can take place in any direction, but we're going to focus specifically on ellipses that are elongated either horizontally, so horizontal ellipses, and vertical ellipses. If we were to rotate and have elongation diagonally, that's going to adjust our equations a little bit. So we're just going to focus on horizontal elongation, which would look like this, versus vertical elongation, which means the longer version of the ellipse is going to be vertical. Okay, so let's focus on some of the key features, and these are going to be the features we find each time we graph. So we'll look at these algebraically, and then that will translate to our graph. So the line segment that passes through the foci, so imagine drawing a line segment passing through both of those particular points, and the actual center of the ellipse, which is going to be between the foci, is what we call the major axis of the ellipse. And then the ellipse's center represents the midpoint of the major axis. So essentially the major axis goes from one far end to another far end of the ellipse. It passes through the foci, and then the halfway point on the major axis, the midpoint of that particular segment, is the true center of the ellipse. Now this segment intersects the ellipse at what we call the vertices. So the end points of our major axis are referred to as the vertices of our ellipse. And then if we were to take the major axis and draw a perpendicular line segment that also passes through the center, passes through that major axis through the center and is perpendicular to it, we refer to this as the minor axis. So how the major and minor axis, and then of course the vertices, the endpoints of the minor axis, are oriented depends on the type of ellipse we have. So if our ellipse is elongated horizontally, that means our major axis is going to be horizontal, and then our minor axis is going to be vertical. And then if our ellipse is elongated vertically, then our major axis is going to be vertical, and our minor axis is going to be horizontal. Now, how do we determine which kind of ellipse we have? That's going to be based on the actual equation we have. So we're going to focus on some key values in our equation, and that's going to tell us which of these two types of ellipses we have. Okay, so we're going to start by assuming we have two values, what we're going to call A and B, specifically where A is greater than B. So the length of the major axis is defined as 2 times A, and the length of the minor axis is defined as 2 times B. So A and B are going to come from the equation for our ellipse. So if we have a horizontal ellipse, our equation is going to be of the following form. It's going to be of the form x squared over a squared plus y squared over b squared is equal to 1. Okay, so what's going on with the a and b here? Well, remember we said a has to be greater than b, so our denominator is a squared, this denominator is b squared, but because a is greater than b, specifically the denominator for x squared is the larger of the two denominators. So if the term with x squared has the larger of the two denominators, that's our indication that we have a horizontal ellipse, that it's elongated horizontally, or more specifically that our major axis is going to be horizontal. And in this case, it's going to be located along the x-axis. Now, if we were to flip these values, if x squared is then divided by our smaller denominator, and y squared is divided by our larger denominator, then we have a vertical ellipse. So in the case where the denominator for y squared is larger, we're going to have elongation vertically speaking, which means our major axis is going to be vertical, specifically along the y-axis. Now in both of these cases, the center for our graph is going to be at the point 0, 0. It's going to be at the origin. And we'll talk about what happens when that moves after we do a couple examples of one centered at the origin. So we also need to determine all of those other key values, those other key points that are located on our graph. They're going to help us get a more accurate graph. So if we start from the center and work our way outward along the major axis, the first pair of points we encounter are going to be the foci. So the vertices are further out, they're along the actual curve. The foci, think of those like the two centers you have in order to draw the ellipse. The foci are going to be between the center of the ellipse and the vertices, which are along, again, the edge of the ellipse, the actual graph itself. Now, how we find the location for the foci is going to involve a little bit more. So we're going to need a and b, specifically a squared and b squared. So we're going to define a third value, what we call c, as the difference between a squared and b squared, and then the square root of that value. So remember what a squared and b squared is. A squared is always going to be the larger value, b squared is always going to be the smaller value, and that may be associated with x squared or y squared depending on which case we are in. So in the case of a horizontal ellipse, our foci are oriented horizontally away from our center. So if we change our x values, increase by c, and then decrease by c horizontally, then we end up at our foci. So we have two foci. The first one is going to have the coordinates c, comma, 0. So in other words, c units in the positive direction horizontally. And then the second of the foci is going to have the coordinates negative c, comma, 0. In other words, negative c units horizontally. Now, if we have a vertical ellipse, that means elongation is vertical. It means our major axis is vertical. It means the foci and the vertices are going to be distributed vertically. So C is defined in the same way. We find it using different denominators in this case. But in this case, in order to get to our foci, we transition vertically, either up or down from our center. So the x value for our center is going to remain constant, and then we're going to add on c and subtract c from the y value. So the coordinates for the foci will be 0, c, and 0, negative c. Now once we pass our foci and we actually get to the graph of the ellipse along the major axis, that's where we find our two vertices. So if our ellipse is horizontal, it's elongated in the horizontal direction, we're going to go a units in either direction away from the center. So if the length of the major axis is 2a, that's a units in either direction for a total length of 2a. And again, we're moving horizontally away from the center, so the x value is changing and the y value is remaining constant. So our vertices are going to be at a, comma, 0 and negative a, comma, 0. Now if we have a vertical ellipse, our foci are distributed vertically, so our vertices are also distributed vertically. A units above and A units below our center. So the coordinates are going to be 0, A, and 0, negative A. Now once we get to the minor axis, the orientation flips. If our major axis is horizontal, then the minor axis is going to be perpendicular to that, which means it's going to be vertical. So if we distribute things horizontally to find our foci and our vertices, we distribute points vertically in order to find our minor axis endpoints. So the length of the major axis is 2A, so A units in either direction away from the center. The length of the minor axis is 2B, which means B units in either direction from the center. But in this case, it's going to be B units vertically in either direction. So our X coordinate is going to stay constant, and then we're going to transition B units vertically, B units up and B units down. So our minor axis endpoints are going to be 0B and 0, negative B. And then if we're looking at a vertical ellipse, if our major axis is vertical, then our minor axis, which is perpendicular to that, is going to be horizontal. So that means our Y coordinate is going to be held constant, and then we're transitioning B units in either direction horizontally. So that's going to be B, comma, 0, and negative B, comma, 0. Now, I'm going to strongly discourage you at the get-go from trying to memorize these formulas, because we have formulas for ellipses, we're going to have formulas for the other two conic sections we're going to look at, and trying to memorize the formulas is not going to be beneficial. It's going to be more helpful just to understand the structure of the graph. How are all the points related to one another? Once you have A and B, you have essentially everything you need. The only other definition you're going to need is going to be the definition for C, based on how A squared and B squared are defined. But past that, it's not a good idea to try to remember formulas for how the ordered pairs are defined. It's better to get a sense of what the graph is going to look like in terms of its shape and make a determination for where these points are going to be in relation to that original shape. So let's look at a couple of examples. Okay, so in this case we want to identify this ellipse's center, its vertices, its foci, and then the endpoints of the minor axis, and then we'll graph from there. So we always want to start by identifying A, B, and C. And based on that, we also need to determine, is this going to be a vertical ellipse? Is this going to be a horizontal ellipse? So let's focus on that first. So immediately I'm comparing these two terms. I know this is an ellipse based on the form x squared over a number plus y squared over a number is equal to 1. That's what tells me I'm looking at an ellipse. And in this case, I notice that x squared has the larger denominator. So because x has the larger denominator, that means we're looking at a horizontal ellipse. So that means when we graph this ellipse, the major axis is going to be horizontal and the minor axis is going to be vertical. So that tells us a lot about how we're going to find all of these individual points in order to graph. Okay, so A is always defined as the square root of the larger denominator. So be careful here though, A is not 16 and B is not 9. This is A squared and B squared. So you might want to take a moment to actually write that out. So A squared is going to be 16 and B squared is going to be 9, which means A is going to be the square root of that, which is 4. It's always going to be a positive number since we're talking about a distance from the center of the ellipse. And then B is going to be the square root of 9, which is 3. Now C, the other value we need, is defined as A squared minus B squared, which in this case is going to be 16 minus 9, and then we take the square root of that. So 16 minus 9, what's that going to be? That's going to be 5, right? No, 7. What am I talking about? 16 minus 9. Let's not make silly mistakes. Square root of 7. There we go. So that's going to be the distance in order to get to the foci. So our center, based on the form of our equation, is going to be 0, 0. Okay, so as I find individual components of the graph, I'm going to add those to my graph. So we have a center at 0, 0. And again, we made the determination that this is going to be a horizontal ellipse, which means that from the center, the longer axis is horizontal, and then the shorter axis is vertical. Okay, so as we transition out from the center, the first points we find along the major axis are going to be the foci. So the foci are going to be C units away in either direction, in this case along that horizontal major axis. So C units in the positive direction, C units in the negative direction. What are we holding constant in this case? In this case, we're holding the Y value constant, and we're just moving horizontally. So that means when we write the coordinates for the foci, they're going to have the same Y coordinate as the center, and then it's just going to be C units in either direction away from the center. So we're starting at 0, 0, and we're going C units horizontally in the positive and negative directions. So horizontally in the positive direction, we're going to add on the square root of 7. So square root of 7, comma, 0. Again, we're holding that Y coordinate constant since we're along the x-axis. And then the focus in the negative direction will be negative square root of 7 and 0. Now, from a practical standpoint, we don't actually need those coordinates to be able to graph, as long as we know where the vertices and then the minor axis endpoints are located. However, if we wanted to draw this ellipse based on the definition, this idea of all the points that are equidistant in terms of the sum of their distances away from the 2 points, those would be the 2 points where we put those push pins in to hold that string, if you remember that picture. So once we transition past the foci along our major axis, that's when we encounter the vertices. So the vertices are going to be along the major axis, further out away than the foci. So each vertex is going to be A units away from the center along our major axis. So in this case, A is going to be 4. So we're going to go 4 units in either direction horizontally away from our center. So 4 units to the right and then 4 units to the left. So that's going to give us coordinates 4, 0 and negative 4, 0. And those are going to be actual points on the graph. So keep in mind, the foci are just given to generate the graph, whereas the vertices and the minor axis endpoints, those are on the actual graph of the ellipse. So the ellipse itself is just the curve we draw. Any points in the center may be used to help us generate the graph, but the graph itself is going to contain the vertices, the minor axis endpoints, and then any points we draw connecting those. So we have a vertex at 4, 0, and we have a vertex at negative 4, 0. So notice it's the same distance away on either side of the center. And if we were to look at the total distance from one vertex to another, that's going to be 8 units, which is going to be 2 times our value for A. So 2A, that's the length of our major axis. Now, if our major axis is horizontal, that means our minor axis is going to be vertical. So B units, in this case, above our center and below our center. So 3 units above the center, 3 units below the center. So that means we're going to hold our x coordinate constant and then increase the y coordinate by b and decrease it by b as well. So that's going to be 0, 3 and 0, negative 3. And so we can put those points on our graph as well. So 0, 3 and then 0, negative 3. And once we have all those points, we have enough to generate a pretty good graph overall. Now keep in mind, this is almost a football-shaped graph. It's not a circle, but it's also not going to be straight lines connecting all of these points. It's a curve that passes through those particular points, in this case centered at the origin. So that is going to be our ellipse. So notice in this case, we didn't need any formulas to find the foci, the vertices, and the minor axis endpoints, aside for that formula for C. Everything is based on just what the graph would look like once we determine whether or not we're looking at something that's horizontal or something that's vertical. Okay, so let's look at another example. So same directions. Now we have a different equation. Now you'll notice this equation is not structured the same way as the previous equation. In order to use what we think of as these formulas, the hallmark of this equation, we have x squared plus y squared. The addition is important. But notice we also have a 1 on the right-hand side of the equal sign. So in this case, we don't have a 1. So what we're going to do in this case in order to put this in a usable form is we're going to take both sides of the equation and we're going to divide by 225. So there would be two ways to generate a 1 on the right-hand side. Either we can divide 225, which is what we're going to do, or you could subtract 224. The drawback to subtracting 224, though, is then you have another constant over here that doesn't seem to be present in our standard form equations. So division by whatever number it is that we want to eliminate is going to put us in the form we want to be in. So I'm going to take each term in my equation, and I'm going to divide it by that number that's currently on the right-hand side, the 225. What we're going to find is that things reduce pretty well based on this division. So I need to reduce all of that, reduce each of my coefficients, everything in the numerator, everything in the denominator. So 225, is it divisible by 25? So 225 divided by 25, that gives us a 9. So that means the 25 reduces to 1, and the 225 reduces to 9, which means I'm left with x squared over 9. Well, similarly, that means if I divide in a 9 to 225 to reduce the second fraction, I end up with a 25. So our 9 reduces to 1, 225 reduces to 25. So plus y squared over 25. And then the goal of all this, dividing 225, was to get a 1 on the right-hand side of the equal sign. And that does that for us. So based on our standard form, this is what we're going to base all our values on. Notice in this case that y squared has the larger denominator. So because y squared has the larger denominator, that means we're looking at a vertical ellipse. Our ellipse is going to be oriented vertically, which means the major axis is vertical, the longer axis is vertical, and the shorter axis, the minor axis, is going to be horizontal. So let's find our values for A, B, and C. So in this case, A is always determined by the larger of the two denominators. So if our larger denominator is 25, that's going to be A squared. That means A is going to be the square root of that, which is 5. B squared is our smaller denominator, so B is going to be the square root of that, which is 3. And C is always defined as the square root of the larger denominator minus the smaller denominator. So 25 minus 9, and then take the square root. And clearly, because I can't do anything like that in my head anymore, let's subtract, and we get 16. So the square root of 16. So whereas with the last value of C, we ended up with an irrational number, here we have a number where we can actually take the square root, and we get that C is 4. So once we have A, B, and C, we have essentially everything we need to know in order to draw this ellipse. So our center is still the origin based on the structure of our equation. Now I'm going to put that in there, and then in relation to the center, we're going to determine what happens for our foci, for our vertices, and our minor axis endpoints. So now we're talking about a vertical ellipse, which means the foci and the vertices are distributed vertically away from the center. So that means when we write the coordinates for those points, we're holding our x value constant at 0, and then the y value is what we're changing in order to find our coordinates. So we'll start with the foci. Those are going to be C units in either direction away from the vertex. In this case, C units above and C units below. So we hold our X value constant, and then 4 units above and 4 units below. And again, we don't actually need those points in order to generate the graph, as long as we have the vertices and then our minor axis endpoints. So our vertices are going to be A units away, vertically above and below our center. So holding that X value constant, and then A units above, so 0, 5, and A units below, so 0, -5. So let me add that to our graph. So 0, 5, and then 0, -5. And again, notice if you take the distance between our two vertices, it's going to be a total of 10 units, which is 2 times our value for A, which was 5. Now, if our major axis is vertical, that means our minor axis is horizontal. It's going to be B units away from the center to get to the endpoints of the minor axis. So that means we're now holding the Y coordinate constant, and we're just changing the X coordinate. So 3 units in either direction, both left and right. So that's going to be 3, 0, and -3, 0. And so I'm going to add those to my graph. So 3, 0, and -3, 0. Then I connect my dots, and again, it's kind of a football shape, and there's our ellipse. So that gives us a couple examples of what's going to happen when we have an ellipse centered at the origin. So we looked at one example where our equation was already in standard form, and then in this case, we had to do a little bit of additional algebra in order to put it in standard form. So now we're going to talk about what happens when our ellipse is no longer centered at the origin. What happens when we have a new center that's somewhere other than the origin, either along one of the axes or within one of the actual quadrants. We're going to define A and B in the same way. What's going to change is now the structure of our equation. How we find the foci, the vertices, the minor axis endpoints, that's not going to change though. So we're going to have what looks like new formulas, but again, if you fall back onto what the graph is going to look like and how the points are distributed away from the center, then again, you don't have to memorize any formulas, and you can just base it on what we expect for the graph. So again, A is defined as being greater than B. The length of the major axis is still going to be 2A. The length of the minor axis is still going to be 2B. We also make the same determination for horizontal versus vertical in the same way. What's going to change is our X term and our Y term. We're going to add a little bit more on there. So a horizontal ellipse is going to be of this form. So X minus H, quantity squared, divided by A squared, plus Y minus K, quantity squared, divided by B squared, is equal to 1. And again, same way of determining whether or not we're looking at something horizontal. In this case, we have a horizontal ellipse when the denominator for X minus H squared is greater. So if X has the larger denominator, it means we're looking at something horizontal. So you can probably guess what's going to happen for a vertical ellipse. Same general structure, so X minus H squared, but now that denominator is going to be B squared, the smaller denominator, and then Y minus K squared is going to have the larger denominator of the two. So in this case, we have a vertical ellipse when Y minus K squared has a larger denominator. Now, the most important thing that's changed here is the center. By subtracting these values from our variables X and Y, that essentially represents a shift. So a horizontal shift, left or right, and then a vertical shift up and down. So the new center for our graph is going to be the ordered pair h, k in either situation. Now, which one has a larger denominator doesn't have any effect on what the center is. The center is just based on what's subtracted from x and then what's subtracted from y. Now, keep in mind if it's x plus a number or y plus a number, we treat that as subtraction of a negative, which means we then have negative coordinates. So because there's subtraction as part of the formula, we treat the actual values themselves being subtracted as positive numbers. So if we're subtracting, for instance, a 1, that means h is a positive 1. If we were adding a 1, that means we're subtracting a negative 1, which means h would be negative 1. Now our definition for C is going to be the same. And again, if we're talking about a horizontal ellipse, we're talking about a major axis that's horizontal. The only difference now is we're starting from a new center. But how we distribute the new points is going to be the same. So if we're starting with a particular center and we have a horizontal major axis, then that means our foci are distributed horizontally away from our center, C units in either direction. So that means we're going to hold our y-coordinate constant. Now it's no longer a 0, it's now the value k, whatever that happens to be. So we're going to hold that value constant because we're just moving horizontally. We're moving C units away from whatever the value for h is. So C units in the positive direction and C units in the negative direction. So that means the coordinates for our foci, again, we're going to hold the y value constant because we're just moving right and left, and we're moving right and left from h by C units. So h plus C, comma k, and h minus C, comma k. Those are going to be our coordinates. Now, what if we have an ellipse that's vertical? Well, now our foci are above and below our center, which means we're holding our x-coordinate constant, and then we're increasing and decreasing the y-coordinate by C units. So the x-coordinate is held constant because we're just moving vertically along that major axis. So it's going to be k plus C, and then h, comma, k minus C. Now the vertices are essentially found the same way. If we're looking at something that's horizontal major axis, that means the vertices are distributed horizontally away from the center by A units. So from our x-coordinate, we're adding on A units, keeping the y-coordinate constant, and then we're also subtracting A units, then keeping the y-coordinate constant. If we're looking at a vertical ellipse, our vertices are distributed vertically. Okay, so A units above, A units below. So we hold the x-coordinate constant, and then just A units added onto our y-coordinate, A units subtracted from our y-coordinate. So constant x, and then k plus A, constant x, and then k minus A. And then as before, it switches when we're looking at the minor axis. So if our ellipse is horizontal, we have a horizontal major axis. That means the minor axis is vertical, passing through our center. So B units above, B units below the center. So in this case, we're holding the y-coordinate, above and below, which means we're changing the y-coordinate, apologies. We're going to keep the x-coordinate constant and add and subtract from the y-coordinate. So h, comma, k plus b, and then h, comma, k minus b. So notice as we transition from something that's along the major axis to something that's along the minor axis, we're changing the other coordinate, one versus the other. So when we're looking at a vertical ellipse, a vertical major axis, that means our minor axis is going to be horizontal. which means we're going to hold our y coordinate constant and then add to x and then subtract from x away from that center. So h plus b, comma k, and then h minus b, comma k. So you can probably see already how memorization of something like this would get very, very complicated. And again, that's why we want to avoid memorization when we can and just think a little bit more about the structure of the kind of graph we're looking at. Starting by finding the center and graphing the center is going to make your life a lot easier. Okay, so let's look at an example where we're no longer centered at the origin. Okay, so we want to identify the ellipse's center. In this case, it's not necessarily going to be the origin. And then the same components again, so the foci, the vertices, the minor axis endpoints, and of course we need to know the orientation of our ellipse. Okay, so we have x minus 3 squared over 16 plus y plus 2 squared over 25 is equal to 1. So we're already in standard form, but I notice that I have values subtracted and added directly from my variables, which means we've shifted the location of the center and shifted the rest of the graph as a result. So remember, when we look at the standard form, we have subtraction as part, that should be an h, and the y minus k. We have subtraction as part of our terms. So the actual value being subtracted is considered to be positive, whereas in this case where we have an addition, that would be subtraction of a negative. So when we write the coordinates of the center, essentially it looks like we're going to flip the signs from what we see in the actual equation. So the x coordinate for the center is going to be positive 3, and the y coordinate for the center is going to be negative 2. So let's add that to our graph. So the center is at 3, negative 2. Okay, so from there, are we talking about a vertical or a horizontal ellipse? Well, in this case, the y term has the larger of the two denominators, which means we're now looking at a vertical ellipse. So before we look at the actual values, let's just think from a structural standpoint. We're talking about a vertical ellipse, which means we're looking at a major axis that's vertical. That means the foci are going to be above and below. In other words, we keep the x coordinate constant and just increase and decrease the y coordinate. And then the vertices, same kind of thing. So keep that x coordinate constant, increase, decrease the y coordinate. If that's the case for the major axis, that means the minor axis is going to be horizontal, which means we're going to hold the y coordinate constant and then add on to x and then subtract from x based on whatever our value for b is. So after that, it all comes down to a and b and then what we find for c. So a is always related to the larger of the two denominators. In this case, the larger denominator is 25. So a is going to be the square root of 25, which is 5. B is going to be the square root of 16, which is 4. So C is going to be the square root of the larger denominator minus the smaller, a squared minus b squared. So in this case, 25 minus 16. And then 25 minus 16 is going to be 9, so square root of 9, which is 3. So that's our value for C. Okay, so this is going to give us what we need to know about the foci. So again, let's go back to the actual graph. Let's think about what we're looking at. So we have a vertical ellipse, which means the foci are above and below this particular central point. So that means we're going to hold the x value constant, and then add on and subtract from the y coordinate, but no longer starting at 0, 0, starting at this center. So here's a good way to write this rather than having to figure it all out at one time. We're going to hold the x coordinate constant, and then from the y coordinate at the center, we're going to both add and subtract our value for C. And so those two different y values we get from doing that, those represent the locations for our foci. And so by writing it in that way, we then can break it up and find the two individual points. So notice they're both going to have an x-coordinate of 3, and then one y-coordinate is going to be -2 plus 3, which is going to be +1, and then one y-coordinate is going to be -2 minus 3, which will be -5. And so those are going to be our foci. And then we're going to leave those off the graph, just focus on the vertices and then the minor axis endpoints. So vertices distributed in the same way. If the major axis is vertical, the vertices are A units above and A units below our center. So we're keeping the x coordinate of our center constant. We're just changing the y coordinate, which starts at -2. And then we're going to add A, we're going to subtract A, so plus or minus 5. So that 3 is held constant. -2 plus 5 is going to give us 3. And then -2 minus 5 is going to give us -7. And so those are going to be the coordinates of our vertices, the endpoints of that major axis. So let me put those on there. So 3, 1, 2, 3. And then 3, 1, 2, 3, 4, 5, 6, 7. And it's worth checking. They should be equidistant from the center. And if we look at that total distance, 5 units and then 5 additional units, that's going to be 10 units total. And our major axis is supposed to have a length of 2 times A, 2 times 5, which is 10. So those make sense. Now our minor axis endpoints, if we have a vertical ellipse, the minor axis is going to be horizontal. So B units to the right, B units to the left. In other words, we're holding the y constant and then just changing the x coordinate by B units. So from the center, 3, -2, we're changing the x coordinate by B units. So starting at 3, we're going to add on and subtract B, which is 4. And then we're going to hold the y coordinate constant. And so breaking that up, 3 plus 4 is going to give us 7, so 7, -2. And then 3 minus 4 is going to give us -1, so -1, -2. So let's put those on the graph and then we should have enough. So 7, -1, -2, and then -1, -1, -2. And again, double check, equidistant from the center, that's 4 units in either direction, a total distance of 8 units between them, which is 2 times B, which is exactly what we expect to get. So those are going to be the points for our ellipse. So connecting the dots, and there we go. Okay, so let's look at one additional special case in terms of the structure of the equation. So the second example we looked at that was centered at the origin, remember we didn't already have an equation in standard form, so we had to do a little bit of work to put it in standard form. In that case, all we had to do was divide out the number on the right hand side of the equal sign in order to get a 1, and that put it in the form we wanted. Now it's going to be a little bit more complicated if we're looking at something where we have something added or subtracted from our x and our y. Sometimes that's going to require a little bit more in order to get the equation in the form we want. So what we have to keep in mind is the most general form of a conic section equation is going to be the one involving h comma k. And most importantly, it is a factored form. So if we think of x minus h and y minus k as factors, then the standard form for each of our ellipse equations is going to be a factored form. Now, not every equation we see representing an ellipse is factored already. We may have an equation that represents an ellipse where we graph it, but it may not be in that standard factored form to start with. It may be in an expanded form. In order to determine, number one, that it is an ellipse, And number two, all of those key components that come from the standard form, we have to convert it to standard form. And we do this using a procedure that we call completing the square. So you may or may not be familiar with completing the square. Completing the square is a technique that we can use to solve a quadratic equation. Well, in this case, we're just looking at two variables that happen to be quadratic rather than just one. And in most cases, we're going to have to complete the square twice. We're going to go through the procedure for x. We're also going to go through the same procedure for y. So before we look at this in the context of our actual ellipses, let's just do a problem where we complete the square in general. Let's just review how this works in general. So we want to solve this equation by completing the square. So potentially this could be factored like it normally would be. Completing the square is just another option for solving an equation like this. So you can potentially factor. When in doubt, you can always use the quadratic formula, and then completing the square is a third option. So let me just write the equation down as is, no changes. So 4x squared plus 40x minus 5 is equal to 0. And it's in the form we would need it in order to factor. We have everything on one side, we have 0 on the other side. Now when we complete the square, we're going to have to take it out of this form just a little bit. Specifically, if I have a constant, I'm going to move it over to the other side of the equation so that everything on the left-hand side is a term involving x. So that's going to give me 4x squared plus 40x, and then I'm going to add the 5 and move it over. Now the next thing I'm going to do is factor out whatever happens to be in front of our quadratic term on the left-hand side. So in this case, the quadratic term has a coefficient of 4. I'm going to factor that out from both terms on the left-hand side. So that's going to give me 4 times the quantity x squared plus 10x. And all of that is equal to 5. Now, the next step is where I actually complete the square. So essentially the idea is I want to create a trinomial here in parentheses that factors in a very specific way. So what I'm going to focus on is the coefficient on x. I'm going to manipulate this coefficient in such a way to create a new constant that's going to be added on to both sides of the equation. So here's the constant. I'm going to take whatever this coefficient is, I'm going to divide it by 2, and then I'm going to take that whole result and I'm going to square it. So what is that number actually in this case? Well, 10 divided by 2 is going to be 5, so that's going to be 5 squared, which is otherwise known as 25. So inside parentheses, where I want to create a trinomial, a specific kind of trinomial, I'm going to add on that 25. Now the 4 is still on the outside, and I'm going to leave it on the outside. I'm just going to add in that 25 inside the parentheses. Now, whatever I do to one side of an equation, I have to do to the other side in order to keep things in balance. And I have to be careful here, because I added on a 25, but I didn't really add on a 25. I added on 25 inside parentheses, but everything inside parentheses is also multiplied by this 4 on the outside. So really, I added on 4 times 25. So when I balance out the equation on the right, I have to take that into account by adding on the 4 times the 25. Because again, it wasn't just a 25, it was 25 that was then multiplied by 4. So I have to do the exact same thing on the other side. Now, what happens? In this case, what we now have is something that factors in a very specific way. This trinomial right here is what we call a perfect square trinomial. In other words, it factors as a binomial squared, a single binomial. So when we factor trinomials, typically we have a combination of two different binomials. In this case, the two different binomials aren't in fact different, it's actually the same binomial. So we're looking for numbers that multiply to give 25, that also add to give 10, and those two numbers would be positive 5 and positive 5. So when we write the factorization of that trinomial, it's x plus 5 times itself, otherwise known as x plus 5 squared. And then on our other side, 4 times 25 is 100, 100 plus 5 is 105, and that's really all we need from there. You could finish by dividing the 4, taking the square root, isolating x, so on and so forth. What we really want to focus on, though, is what we added on and how we balanced it out on the other side before factoring. So the factorization, you're just factoring a trinomial like normal. It just so happens it's going to factor in this particular way. But knowing what to add on and knowing how to balance it out on the other side, that's going to be the most important thing in this case. So this procedure, this is what we call completing the square. Once we add on this value, we complete that trinomial to make it a perfect square trinomial that factors in this particular way. So we're going to do that whenever we encounter an equation that potentially represents a conic section, but isn't in the kind of form we want, where it's pre-factored, we have those denominators, we have one on the other side of the equation. So let's look at one like this that is not in the form we want yet, that we need to put in the form we want. So notice I have an x squared, I have a y squared. My indication that this is an ellipse is based on the fact that both of these terms are positive. The x squared term is positive, the y squared term is positive, they're added together. That's my indication that I'm looking at an ellipse versus some other type of an equation representing a different type of graph. But notice neither of these are in a factored form. We don't have anything x factored, anything y factored. We've got a linear x term, a linear y term, and then a constant. So essentially, I need to do what I did here, but I need to do it both for x and for y. So I'm going to do a couple things in the first step. So notice here, first thing we had to do was move that constant over. So in this case, we're moving the 10 over. And then I'm going to rearrange things a little bit so that all of the x terms are together and all of the y terms are together. So do a couple things in one step. So just looking at my x's, I have 3x squared, and then I'm going to rearrange it so that the 6x is right next to that, since those terms are going to go together when I factor. And I'm going to go ahead and put parentheses around it so I know that those are grouped together. Now to that, we are adding on 7y squared, and then we have a negative 28y that also will be combined when we factor. And so that's going to be grouped as well. And then the 10 is going to be moved to the other side of the equation. It has to be subtracted, so that's now going to be a negative 10 on the other side. Okay, so once we moved our constant over, notice we factored out whatever coefficient was in front of that quadratic term. So we need to do that here, but we need to do it both for the x's and for the y's. So whatever the coefficient is for my quadratic term in each set of parentheses, I'm going to factor it out of that set of parentheses. So the first set of parentheses for x, we're going to factor out a 3, which is going to leave me with x squared plus 2x. And then in the second set of parentheses, I'm going to factor out a 7, which leaves me with y squared minus 4y. And as of right now, I haven't added on anything. I'm just rewriting things in a different form. So the right-hand side is still negative 10. So now we're going to actually complete the square. Within each of these sets of parentheses, we're going to add on whatever we would need in order to get something that factors the way this did. So remember, we're going to take our coefficient for the linear term, we're going to divide it by 2, and we're going to square it. So 2 divided by 2 gives me 1, and if I square that, 1 squared is going to be 1. So inside this set of parentheses, I'm going to add on a 1. Okay, now for the next set of parentheses, we have a negative 4. We're going to divide it by 2, which gives me negative 2. And then we're going to square that, which gives me a positive 4. So keep in mind, we're squaring a number each time. You square a positive, you get a positive. You square a negative, you also get a positive. So the additional term we're adding on is always going to be truly an added term. It's not going to be subtracted. So negative 4 divided by 2 is negative 2. Negative 2 squared is positive 4. So y squared minus 4y, and then we're going to add on that positive 4. And now that we've changed the left-hand side, we need to balance it out on the right-hand side. So in the first set of parentheses, we added on 1, but it was a 1 multiplied by a 3. So we need to add on 3 times 1. And then on the other side, we added on a 4, but it was really a 7 times 4. So we need to add on 7 times 4. Okay. Now these two are perfect square trinomials, 1 in x, 1 in y, and we're going to factor those, leave our coefficient out there. So two numbers that multiply to give 1, that also add to give 2, well that's going to be positive 1 and positive 1, so this factors as x plus 1 squared. Now two terms that multiply to give 4, that also add to give negative 4. Well, if they multiply to give a positive number, all that means is that they're the same sign. So they could both be positive or they could both be negative. In this case, because they multiply, or excuse me, they add up to give a negative, they both have to be negative. So those two numbers that multiply to give positive 4, add to give negative 4, that's going to be two negative 2's. So y minus 2 squared. And then we just need to clean it up, combine all of that on the other side, and of course you can do that in the calculator. So negative 10 plus 3 times 1, which is 3, plus 7 times 4, which is 28. And that's going to give us 21. Okay, so we're almost there. But remember, we need to have a 1 on the right-hand side in order to be in standard form. So this is similar now to the problem we worked before where we had to put it in standard form. Whatever number we want to turn into a 1, we're going to divide by that number, all three terms, and that's going to put us in standard form. So we're going to reduce those values. So 3 divides into 21 7 times. So we now have a denominator of 7. So x plus 1 squared over 7. Plus 7 goes into 21 3 times, so our denominator is now 3. So y minus 2 squared over 3. And then 21 over 21, the goal was to get a 1, and we do get a 1. So this is going to be the actual standard form equation we're graphing. And because these two terms are added, that's our indication that we're talking about an ellipse versus some other type of graph. But in this case, what's our A, what's our B, what's our C? Because notice our denominators, they are not perfect squares in this case. The larger denominator goes with x, which means we have a horizontal ellipse. It doesn't matter that they're not perfect squares, it's just which one is larger, which one is smaller. So larger denominator goes with x, that means we have a horizontal ellipse. Now, a squared is 7, which means a is going to be the square root of 7. B squared is 3, which means b is going to be the square root of 3, which means unfortunately we don't have very pretty numbers here, so graphing is going to be a little bit more of a challenge. Now c is always defined in the same way. It's going to be the square root of a squared, which is 7, minus b squared, which is 3. So square root of 7 minus 3, which is the square root of 4, which is 2. So in this case, c actually worked out well, a and b did not. So what is our center based on our standard form? Well, we have x plus a number, y minus a number. So that means the x coordinate is negative, we flip the sign, and the y coordinate is positive. So our center is going to be -1, 2. Okay, so let's put that on our graph, a center at -1, 2. And we know we're talking about a horizontal ellipse, so that means our longer axis, our major axis, is going to be horizontal. It means the foci are distributed horizontally, and the vertices are distributed horizontally as well. So for our foci, we're going to the right of the center, we're going to the left of the center, which means the x-coordinate is changing and the y-coordinate is being held constant. So adding on c to our x-coordinate and subtracting c from our x-coordinate. So -1 plus or minus 2, and then hold our y-coordinate constant. So -1 plus 2 is going to be 1, so 1, 2. And then -1 minus 2 is going to be -3, so -3, 2. So those are going to be our foci. And unfortunately, those are going to be the easiest ones to graph, and they're the ones we don't actually need to graph. A and B are a little bit nastier, which means our vertices and then our minor axis endpoints are also going to be a little bit nastier. So let me flip over, and I'm going to rewrite those values. So A was the square root of 7, and B was the square root of 3. Okay, so what about our vertices? Let me also make a note of our center. Our center is -1, 2, and we can see that from our graph. So we have a horizontal ellipse, which means our vertices are to the right and left. In other words, we hold the y-coordinate constant and just change the x-coordinate, add on a, and then subtract a. So we have -1 plus or minus a, which is the square root of 7, and then we're going to hold the y-coordinate constant at 2. Now, what does this actually mean, though? Well, these are the exact values. So if we split this up into -1 plus root 7 and -1 minus root 7, those are the actual x-coordinates for our vertices. But those are not going to be particularly easy to graph. So for purposes of graphing, ideally we want to approximate what those two x values are going to be. So our first x value is going to be -1 plus the square root of 7, which is approximately 1.6. We'll call that 1.6. So 1.6 and 2. Now we also have a vertex with an x-coordinate of -1 minus the square root of 7, which comes out to about -3.6, and then 2. So that's how we're going to graph. We're going to graph from that point of view. So notice again the y-coordinates are the same. What changes is the x-coordinate. So 1.6 and 2, so about halfway between 1 and 2, and then up 2 units. And notice it's along the same line with the center, which is to be expected. And then -1, -2, -3, somewhere between -3 and -4, about halfway, and then up 2 units. But notice again, equidistant from the center, which again is what we expect to see. Now, same kind of thing for our minor axis endpoints, which are going to be above and below our vertex. So we're going to keep the not the vertex, the center. We're going to keep the x-coordinate constant and then add and subtract from the y-coordinate for our center. So we're going to have -1, keep that constant, and then above and below, so 2 plus or minus the square root of 3. And just like with the vertices, that gives us exact values, but for purposes of graphing, we need to approximate each of those new y values. So 2 plus the square root of 3 is going to be about 3.7. And then 2 minus the square root of 3 is going to be about 0.3. We'll call it that. And again, notice they have the same x-coordinate because they're in line with the center vertically speaking. So -1, 1, 2, 3, about 3.7, so close to 4, but not quite. and then -1, 0.3. So just a little bit above the x-axis. So that's going to be our graph. That's about as accurate as we can get with the level of detail we have. So there we go. Okay, so just to recap, we talked about in general what a conic section is, and this was our introduction to ellipses. So we've looked at ellipses centered at the origin, either vertically or horizontally distributed, and then also ellipses where the center has shifted, also vertically and horizontally distributed. So as we change the standard form, make small changes to the standard form equation, we can end up with different types of graphs. So the next type of graph we're going to look at is called a hyperbola. The equation is going to look very similar to the equation for an ellipse with one specific difference.